Bismillahirrahmanirrahim. Good afternoon, everyone. Today, our lecture will be about the current and reverse bias. Let's start from this question. Let's try to solve it. Calculate the current at reverse bias diode, or we can say prove reverse bias current equal minus saturation current. From this circuit here, minus with positive terminal, that's mean reverse bias. Let's start from Schottky equation. The current equals saturation current exponential, the constant alpha dot V minus 1 at reverse bias. V will be negatively a big amount, that's mean minus infinity. Here we will put this value instead of V at Schottky equation, and will be I equals saturation current exponential minus alpha infinity minus 1, that's mean minus infinity will be 1 divided on exponential infinity to be like that, and after that will be 1 divided on exponential infinity equal infinity. 1 divided on infinity equals 0. That's mean I equal minus saturation current, or we can say IR reverse current equal minus saturation current. This will be important. Let me write this. At good diode, saturation current will be equal picoampere. That's mean minus 12 ampere. And at bad diode will be related with minus 6 to exponential minus 9 ampere. And at this diagram, this curve will be at the third part, minus minus. After that will be something like linear. This is the saturation current. Like I said before here, reverse current equal minus saturation at reverse bias. Now let's work on forward bias. Calculate the current at forward bias diode, or prove forward bias diode current equals saturation current exponential alpha V. Like here, like we're seeing, two terminals here, N terminal with N diode terminal, and the same thing with a positive terminal diode with positive power source. From Schottky equation, I equal saturation current exponential alpha V minus 1 at forward bias, V to equal very big amount, but positively. That's mean exponential V very big. If we compression it with the alpha, that's mean will be exponential V minus 1, and we can ignore it. Ignore the 1 because, like I said before, the equal very big amount will be I equal saturation current exponential alpha V. Like I said it before here, forward bias current. The relation between the current at y-axis and voltage at x-axis like that. At first will be start with like 0 volts. After that will start to increasing from VF, that's mean forward voltage bias, exponentially to be like that. And with reverse bias will be something like linear. And here I R, or we can say I naught minus I naught equal reverse bias current. Let's talk about at ideal diode. Here we was talking about non-ideal current diode. Here at ideal diode, that's mean just theoretical theoretical idea, must be like that, with y-axis, x-axis, forward, reverse bias. Here, let's try to answer this question. Calculate the diode factor at ordinary diode, or prove the diode factor equal approximately 1 but at room temperature. We will calculate the diode factor by using the constant equation. constant diode equation equal charge electron divided on diode factor, Boltzmann constant, room temperature here will be 300 Kelvin. Diode factor equal, that's mean charge of electron divided on diode constant, Boltzmann constant dot temperature. Boltzmann constant, like we know, has two values, 1.38 exponential minus 23 joule divided on Kelvin, or 86.2 dot exponential minus 6 electron volt divided on Kelvin. Here we will dealing with joule divided on Kelvin. That means we will select 1.38 dot exponential minus 23 will be dot 99 exponentially approximately equal 1. Plot the curve between lnI, linear current, at axis and the voltage at y-axis at forward bias. I equal from Schottky diode. This equation is very important to us at the diode topic. I equal saturation current exponential diode constant V minus 1. I equal saturation current exponential diode constant V minus I naught. Let's work on forward bias. That's mean V positively amount and very big, bigger than 0 at high bias region. We can, that's mean will be exponential V, and this amount will be very big amount. That's mean we can ignore minus saturation current to be like that. Let's take two arbitrary points. Let's be V1 and V2, like here, V1 and V2. And sure, V2 will be bigger than V1. We have I1, I2 will be ln1, ln2, sure, with V1, V2. That's mean by using the same equation at forward bias will be I1 equal I naught exponential constant diode V1, and I2 equal saturation current exponential diode constant V2. Here, from the original equation, I equal saturation current exponential alpha V. Take ln to both sides to be lnI equal lnI naught exponential alpha V to be lnI plus ln exponential alpha V. This one of ln characteristic. Now will be lnI will be equal ln saturation current plus alpha V. This will be a star equation. The curve will be linearly, but the theoretically, I will explain that by using the diagram like that. Let me take a few seconds to explain that. Now let's work on at low bias region. At first, we was talking about high bias region here, or middle injection, because high injection will start after V2. The low injection will start from 0 until V1. At low bias region, I equal saturation current exponential alpha V minus 1, Schottky equation. At low bias region, V will be very small amount. That's mean will be approximately 0. Exponential 0 equal 1. That's mean the total I will equal 0. When V equals 0, that's mean I equals 0 from Ohm law, because V equal IR and I equal V divided on R. Then I equal ln 0 equals 0, because that at our diagram we will start from 0, 0 point, because ln 0 equals 0. That's typically, but theoretically we'll start from this point. Ln I naught will be bigger than 0 point. Because that I start from 0 point, like I said before, after that starting to increases at V1. Here, theoretically, low V will be start from this point, ln I0, but typically we'll start from 0, 0. Here, ln I1, ln I2, V1, V2. At ideal diode, we have two kinds of resistance. Number one, statical resistance, or we can say DC resistance. Number two will be dynamically resistance, or we can say AC resistance at ideal diode, because at a non-ideal diode, we will dealing with another kinds of resistance. Here, statical resistance or DC resistance from Ohm law are equal V on I. At reverse, V equal minus value. That's mean I equal, like we know, I equal minus reverse current, and reverse resistance equal minus V divided on minus reverse current, and we can say V equal V on reverse current, like that. At forward bias, V equal positively amount. That's mean I equal positively IF. That's mean forward current. Forward reverse current equal V divided on forward current. Kind number two, dynamical resistance or AC resistance. Let's try to solve this example. Draw the curve between radiation, dynamic resistance and voltage. Dynamic resistance will be at y-axis and voltage at x-axis. From Ohm law, V equal I R, R equal by V on I. And the resistance, the dynamic resistance equal dV divided on di. Or we can say 1 divided on dV on di to minus 1. That's mean equal 1 divided on di on dV. Let's say this equation will be number 3, and let's come back to Schottky diode and take derivation to these both sides. Will be di divided on dV equal d on dV to I naught exponential alpha v minus 1. And will be like that. When I know saturation current is constant and dependent on the kinds of diode, that's mean derivation of constant equals 0, because that will be di or divided on dV equal d on dV saturation current exponential constant diode V. Let's take the derivation to these sides. Will be alpha V exponential alpha V. This will be equation number 4. And let's put it in equation number 3. The dynamic resistance equal 1 divided on di on dV. That will be 1 equal 1 divided on alpha saturation current exponential alpha V. Like we see here, let's be this equation number 5, and we can say we can write another equation to dynamic resistance. Will be from Schottky equation, I equal I naught exponential alpha v minus 1, and let's take this to the left side to be I plus saturation current equal saturation current exponential alpha v. By that, we can say the dynamic resistance equal 1 divided on alpha diode constant. Instead of these values, we can say, we can write I plus I naught saturation current. Dynamic resistance will change with current only. Why? Because I naught, like we know, is constant. Now let's work on the DR, the dynamic resistance, when V equal negatively huge amount, when equal 0, when equal positively huge amount. Okay, by using this equation, number 6, or number 5, the same. I don't know why I write it two different numbers. That's right, because here the dynamic resistance is related, has relation with V. That's right. That means we will depend on equation number 6, dynamic resistance equal 1 on saturation current, diode constant, exponential alpha V. Let's put here minus infinity and see what will happen. Will be like that. I will put the exponential value with the side to can delete the negative sign. That means here we will be very big amount, but negatively. After that, I will put it up. Let me see something. No, that's wrong. 1 divided on all of these values. Diode constant, saturation current, exponential alpha V. All of these are down, are here. Inside, below 1. I forget it, complete this line to here, sorry. Because that when we put minus infinity, that's mean this side will be very huge, big amount. After that, I will put it up to be positively amount. That's it. Our lecture today is done. Thank you so much. Have a good day.